Welcome everyone to this webinar. It's all about hygienic seals for highest process reliability. This is the second session of our webinar series, and we are proud to welcome you to the second series. Many of you are already acquainted with what we are doing and how the process worked. I will guide you through the general data, the process on the next slide that I will share in a moment. Once again, Rubber Fab Team Europe will welcome you today, which is Dominic, Area Sales Manager, Sasha Butter, which Hello. You can see on the screen right now, Chris Neufer, Application Engineer as well. Okay, so yeah, thanks, and I think we will have some fun in this series today or in the next sessions. So let me share my screen once again. Okay, I will just share some notes with you for the organization of this webinar. All participants, please mute your microphones. Also, please feel free to switch off your video, which will result in better quality of this presentation for you. We will record the session in order to make it available online afterwards. I will send a SharePoint link with you once again after this meeting. And please feel free to raise any question in the chat box area of this call in Microsoft Teams, and we will make sure to either answer the questions in the middle of the presentation or towards the end. So we will also have a small feedback survey. Today we will use Microsoft Forms and share a link with you. You will find that link also when we share the handout by mail after the presentation. Okay, now I want to make the transition to Sasha, who will guide you through today's presentation. Thanks, Sasha, and enjoy.
Thank you, Dominic. So good morning, everyone. Welcome to this webinar. I hope you're doing great. I'm excited for yet another webinar that we have prepared for you. I hope that you enjoyed this webinar and find the information helpful when talking to your customers. For the people on the call that I have not met before, I would like to start by briefly introducing myself. My name is Sasha Butter. I'm 30 years old. I live in Düsseldorf, Germany, and I'm with Rubber Fab for 2 years now, being responsible for the product management in Europe. Before that, I've been with Garlock Sealing Technologies for approximately 4 years as an application engineer and technical consultant. And before that, I have graduated at the University of Krefeld, studying chemistry and biotechnology. And short after at the University and Business School of Cologne for my MBA. Yes, so today I'm your presenter, and we want to focus on hygienic seals for the pharmaceutical industry, some market trends, and process solutions. So let's get started, and I will also share my screen for you. The webinar is called It's All About Hygiene, Hygienic Seals for Highest Process Reliability. So we want to talk about hygienic seals, and in order to do so, I want to give you some insights on the trends, on the developments we have observed on the market. So let's start with faster production. We have observed that the production speed in the pharmaceutical industry has increased significantly in the last couple of years. When talking to process engineers in the pharmaceutical manufacturing plants, they would state something like you see on the slide, the demands of faster production speeds and shorter batch runs are putting increased pressure on process manufacturing requirements, while assuring product safety through the use of automated cleaning processes. So that means that we are finding that many manufacturers are turning to smaller batch runs when producing pharmaceuticals with greater product diversity and more frequent changeovers, so changing the product. As a result, they are under constant pressure to adapt manufacturing processes and to meet the changing production demands in terms of speed, flexibility, and safety, while continuing to comply with a big number of regulations. On top of that, we have observed that there's a shift from batch manufacturing to continuous manufacturing. So there's a shift from batch manufacturing to continuous manufacturing. What does that mean? So if you're not familiar with the terminology batch and continuous manufacturing, let me give you some background information. So batch manufacturing is the most common and traditionally used mode of manufacturing in the pharmaceutical industry for probably more than a century, really. The drugs are produced in a single large bioreactor, step by step. And a typical pharmaceutical batch manufacturing facility is built with an investment of billions of dollars, really. So the production mode is batch manufacturing, meaning that the products are produced in a single large batch, step by step. So the product is taken from step A to step B to step C until you finally have the final product, but you are always operating in batches. So like I said, a facility for batch manufacturing of pharmaceutical ingredients, the investment in those facilities, it's enormous, and it can be billions of dollars. It contains multiple pieces of complicated equipment, and the employment of human labor and multiple transfer steps also poses extreme contamination risks to the user and introduces the possibility of errors. So because of this highly complex manufacturing steps, it's very sensitive to errors. However, the rising demand for pharmaceutical products has caused that flexible manufacturing alternatives, such as continuous manufacturing processes, are being, let's say, more embraced and gaining more and more important in the recent years. Continuous pharmaceutical manufacturing involves a drug taken from its base ingredients. So you feed in the base ingredients, and at the end you receive a final product with no need to hold or stop during the production. So it's really a continuous production. You insert your ingredients, your substances required for manufacturing, and you take out a finished product. According to the Food and Drug Administration, FDA, the pharmaceutical manufacturing industry wastes up to $50 billion every year on average because of inefficient processes. Continuous manufacturing serves to be a potential solution for the same problem, and in addition, there are various other advantages that continuous manufacturing offers. For example, increased productivity, reduced energy, more time efficiency, and of course less waste. So it can be very beneficial for the pharmaceutical manufacturer to move the manufacturing mode from batch to continuous manufacturing. A little bit information on the current development. The FDA is passing at the moment quick approvals to companies transitioning from batch manufacturing to continuous manufacturing procedures. In 2016, so not all too long ago, the substance Orkambi by the company Vertex Pharmaceuticals was the first to go batchless on their production lines. And later on, for example, in 2019, Janssen Pharmaceuticals has switched product lines from batch manufacturing to continuous manufacturing for their API products. And many more are following because of the advantages. At this point, I would like to quote Professor Muccio. Probably you're not familiar with him, it doesn't really matter. He's an expert for pharmaceutical product and process design and a voting member on the FDA Committee for Pharmaceutical Sciences. And he says that continuous manufacturing represents the future of advanced pharmaceutical manufacturing and will produce significant improvements in efficiency, safety, cost, and speed to market. The BCC Research new report on continuous manufacturing for pharmaceuticals shows that the global market was valued $2.3 billion US in 2018, with Europe accounting alone for $664.8 million US in 2017 already. So we are looking at the numbers for continuous manufacturing technology, how this market, what's the size of this market and how it is developing. Further, we see that the market size is also expected to grow further, with an annual growth rate of 8.8% estimated, of course, and through 2024 will reach $3.8 billion. So it's a rising market, and altogether, the more demanding manufacturing requirements that I've mentioned before and the significant market growth, we see as evidence that the industry requires sealing solutions which can keep up with the changing production landscape in the pharmaceutical industry. So let me say there's one common misconception. And the misconception is that today's most advanced cleaning processes that incorporate high temperatures, increased chemical concentrations, flow rates, they may not be enough. We have done internal testing and have also done testing in collaboration with several universities that show that even after a thorough cleaning, you may be obtaining false negative readings in your validation process more often than you realize. We have determined that even the best cleaning processes often only result in inactivating the bacteria and not eliminating it, not killing it. What this means is that while your internal testing, your customer's internal testing may show that bacteria is not present, in fact, it is possible that toxic even or other harmful microscopic biofilms still linger in your system, remain there undetected, and are guaranteed to resurface and contaminate your production when you expect it the least. What's exciting about this is that many manufacturers don't realize that this is happening. When you think back, for every one of you who has joined us in the first webinar session some weeks ago, you might remember this illustration you can see here. It describes the building of a biofilm. And what you can see here, we go through it very briefly again to remind you, but immediately after a production system starts up and it contains microorganisms, always the media, or in most cases it contains microorganisms. Often you need to have microorganisms in there because they're part of your production process, especially in biotech. When you produce vaccines or even antibiotics, your producers are the microorganisms. But even if you don't intentionally add organisms to your systems, there's a high chance that you have some level of, let me say, contamination, that you have some level of microorganisms in your system. And immediately after starting up the system, we see that organisms, but also organic molecules like fat, like minerals and so on, are traveling through your production process. So let's say the areas, the gray areas here are the wetted parts of your production system, the parts, the equipments in contact with the media, for example, the pipe or a hygienic gasket, and the media is streaming by. You will see that shortly after starting the production, approximately 4 to 6 hours after starting the production, we already see this effect, that microorganisms will not just fly by the equipment, but instead some of them will irreversibly adhere to the surfaces. Every kind of surface shows this effect. And after a short time, if more and more of those organisms, organic molecules, fats, minerals, and so on adhere, you will kind of like start that a biofilm is formating. So more and more stuff really from your process gets stuck to this biofilm, more organisms, other substances, and they cause this so-called biofilm to grow in step 3, so that eventually you have a biofilm in your system, undetected, that can grow up to a respectable size really. And when it grows and grows, the danger is that at some point it grows so far that parts, bits and pieces of this biofilm can be taken by the flow of your system and be removed from this formation. And this is a very critical point, but we are going to see that a little bit later. Other negative aspects of having a biofilm is that they interfere with your product quality. Of course, they pose a contamination risk. They might also reduce the heat transfer in several processes, cause increased filtration and friction resistance. Also, what can happen is that we see material destruction, biocorrosion. So you might all know this from sanitary pipes, also in your private use, in bathrooms, in maybe all the bathrooms you have visited, you will see pipe corrosion. And this is indeed happening because of microorganisms in the connection. We can say that more than 90% of all product contact surfaces in a normal pharmaceutical system come from tubes and fittings. And what we have found is that after using standard cleaning processes, a typical gasket can still show microorganisms, so residues on its surface. This may not sound like a lot, but even at this level, future contamination of your system, of your customer system, can be guaranteed. In fact, the development of biofilms is your customer's biggest threat to contamination. And like I said before, the detection of biofilms is not always guaranteed. You will find them when you want and expect them the least. And that is when parts of the biofilm are removed and get into your product, contaminating your highly valuable batch and contaminating your system. So why really is the cleanability compromised? Why don't the standardized cleaning processes, the CIP processes, why do they so often fail? Let me explain to you. So here you can see a typical tri-clamp connection, a very common connection in the food and pharmaceutical industry. You have your two flange ferrules, and in the middle you have a tri-clamp gasket. Here we have the process the inside of the process, and here we have the outside of the process. And what we want to look at is the internal sealing point indicated by this green arrow here. This sealing point, we can also call it the ideal sealing point. It's critical to prevent leakage and the entrapment of media. It kind of is the process interface between the gasket and the ferrule. And it represents the critical point to seal and prevent leakage and entrapment risk, like I said. It also makes sure that the product does not reach between the gasket and the flanges. That's what entrapment stands for. Another challenge for those connections is the exposure to cycles, both thermal cycles and chemical cycles. They will cause the gasket material to expand and to contract again and again, depending on the process parameters. Here we go. And this constant heat and chemical exposure can cause the sealing point, this ideal sealing point, to move. So it basically can cause that the gasket, that the connection is compromised and that we have rather leakage or entrapment risk, meaning media finding its way between the gasket and the flange, where it remains, where it cannot be detected, where it is extremely hard to be removed by common cleaning cycles. And finally, as long as the material is able to maintain its compression set, this is a very important point, the compression set of the gasket will also maintain its ideal sealing point. But because of those thermal and chemical cycles that the whole connection will experience in a manufacturing process, often this results into the gasket losing its compression and therefore losing this ideal sealing point, so that the hygienic connection is not really hygienic anymore. Another cause for a hygienic connection to fail, for no longer be hygienic and therefore compromising the user's process, is uneven loading of the gasket. We see an example of uneven loading right here. So what you see is you see an imprint of a pressure indicating film. So you can install such a film between a gasket connection, then you can install it. You install it by the books, so you use a torque wrench, you of course have all the equipment inspected and so on. And what you can still see that with the most common clamps to install the connection, we have an uneven loading of the gasket indicated by this irregular red color of this film. So you see basically that in the area of the screw of the clamp, here by these two, indicated by the two blue lines, you have a relatively high compression of the gasket, like I said, indicated by the red color. And on the other side, where the coupling part of the clamp is, you also have a relatively high compression of the gasket. But in the areas on the side, we're seeing a lack of gasket compression. We see a lack of load applied to the gasket, and this very often can result in insufficient sealability. Yeah, so the lack of compression can result in insufficient sealability. So we are losing our ideal sealing point in these areas, and we have a high risk that media finds its way between flanges and the gasket. So this is another cause for a hygienic connection to fail, uneven loading of the gasket. Another big factor to consider is the surface quality of the wetted parts of all media contact equipment, really. And you remember the backgrounds of this also from our first webinar, where we have described the hygienical principal criteria. In this case, we want to go one step further. And what you can see here, you can see the microscopic pictures. They are taken with the scanning electron microscope of some very common gasketing materials, for example, EPDM and FKM. We see the surface with the magnification, with 100 times magnification in each and every picture. And you see that the surface, it's rather rough if you magnify and look very close. And you see this is true for EPDM and FKM, but you will also find relatively rough surfaces when you have a look at virginal, traditional PTFE, and silicone as well. With silicone, it's actually not that rough, but in this picture, we can see the separation line really well, which is basically also in media contact and in the middle of the gasketing surface. Yeah, so what rough surfaces will do, they provide a relatively a big surface, first of all, but also because of this big surface, a high free accessible surface energy, which causes an entrapment risk, which causes microorganisms or particles in the system to adhere, to get stuck in these voids and gaps of a rough surface. Whereas on a smooth surface, you wouldn't have this problem because you would have less surface available, you would have less adhesion energy, and therefore a low entrapment risk. And you can prove this, you can have a closer look and have a look at one of those standard gasketing materials using a fluorescence microscope, which kind of shows you that the gasket, in this case an EPDM gasket that was contaminated and afterwards cleaned. Yeah, so it was cleaned within a cleaning in place process, standardized. You would see that even after cleaning, the surface of the gasket still contains a lot of substances. In this case, we actually see microorganisms, the test microorganism really well. And we also see indicated by the different colors that the red parts, they are inactivated. They don't have like a metabolism anymore, but you also see a lot of green and orange molecules, organisms here, which actually are very much alive still and would be able to recontaminate your system. Another topic we had discussed in depth in our first webinar is gasket intrusion. So when a gasket is not really dimensionally stable, or if the gasket dimension was picked wrong in the first place, we have something that we call gasket intrusion, meaning the gasket stands into the process, it reaches into the process, which makes the connection very difficult to clean, which can be the root cause for cross-contamination, because we have like very slow-moving areas. We have like so-called entrapment areas or dead areas in those areas where the gasket intrudes the production system. So this can be a cause for cross-contamination. In extreme cases, it can also be a cause for product hold-up. Of course, it creates certain turbulences, which are indicated by the flow graph you can see right here. So we have very low rates of flow in the areas just before and behind the gasket, and a very increased flow, let me say in the center of the stream. Yes, and this ultimately all causes the cleaning cycles to be less efficient, and it actually causes the risk for contamination of your system. So let's say the customer system is contaminated. What's next? So this is just a rough example, so don't take this too very seriously. Ultimately, each and every pharmaceutical manufacturer knows very well themselves what they have to do and what it means if they actually encounter system contamination. But just to give you a brief idea how this process could look like. In the very first step, it's about finding this bad batch, seeing where does the contamination come from. Do we have pressure loss? Do we see any leakage? This might, depending on the size of the manufacturing plant or the process line, it can actually take up to 1 or 2 days. So let's say you have found the root cause of your contamination. You have to make sure that all components, all critical components are replaced. These are gaskets, but these can also be pumps, diaphragms, any other critical equipment really. And depending on the complexity of your line, it again may take a couple of days until you have all these equipments in place, have identified the root cause for the system contamination. And let's say after step 2, you can actually go ahead and you have replaced the gaskets, components, the media, the cleaning media possibly as well, and you have done that. So later on, with most gaskets, you have then to retorque all gaskets after pressure tests, after letting the system cool down again. let's say it takes a couple of hours only. You again have to clean your system, start the sterilization process when you replace components, when you open the system. Then you want to validate your process, and if you're lucky and you have like automated validation processes or an in-house laboratory, this might be actually quite fast. But again, no guarantee on the times. They may be shorter or faster depending on the capabilities of the manufacturer. You have to do pressure testing, you have to destroy a contaminated batch, and you have to deal with all the internal paperwork. And this is all necessary for system contamination if the contaminated product did not go out to the consumer, if it didn't leave your facility. Imagine how this list would continue if actually contaminated, possibly dangerous products have left the customer's facility, are on the way to the end user. Then we're also dealing with an official callback. The products have to be called back. It will have like disastrous consequences for the image of the company, and we are seeing more and more callbacks happening recently. So basically the question for the end user is really, how much does your batch cost? How much does your shutdown cost? Because they know best what they have to do when they encounter system contamination. But with all this negative news, I'm also here to tell you there is a better way. So there's a hope. And what if we could eliminate most contamination issues by using a tri-clamp gasket that offers the same or better cleanability than the most smooth equipment itself, the pipes? Yeah, so better cleanability than the pipe itself. And not only that, but also with eliminating the need to retorque your connections, meaning a gasket that doesn't need to be retorqued. We have worked with many companies, pharmaceutical manufacturers that were able to save thousands of euros annually by doing so. And this has allowed them to not only reduce contamination related costs, for example, downtime or batch loss, but actually also increase production time and overall product quality. This would be especially interesting in the continuous manufacturing, where high efficiency production for pharmaceutical substances is extremely important, and where the long and reliably safe use of component is extremely beneficial, as you want to operate a continuous manufacturing line without interruption as long as possible. So what if there's a gasket that doesn't show any contamination after cleaning in place processes? We have tested this for our BioPro Plus product. And what you can see here is you see a number of different gasketing materials. And they all went through the same process. So first, they were contaminated on purpose. And after they were contaminated, they were all exposed to a standardized cleaning in place process in a test rig that you can see right here. The testing was done according to EHEG guideline number 2 to simulate the in-place cleanability of equipment. Again, what you can see here, you see the components, and they are all covered by this purple colored media. And what this media does is it basically allows for it allows us to analyze how clean the gaskets are after they have been contaminated and then later on cleaned by a cleaning in place automatic process. It allows us how clean they are after this cleaning cycle. And this purple media, it works like this. If you have any residual contamination, if you have any organisms remaining on your equipment, on your gasket in our case, it kind of works like a color indicator, meaning that after a certain period of time, those gaskets that are still contaminated, they show yellow coloring. So the more yellow color is visible, the more residual contamination was present on the gaskets after the cleaning process. And we can see here that many of the tested gaskets show a lot of yellow coloring, meaning they have not been residue-free after the cleaning in place processes. This, the testing was repeated, of course, numerous times to confirm the results. You just see some pictures here, but you can kind of do a ranking of the gaskets. And the only product, the only material that didn't show any contamination whatsoever, no matter how often the test was performed, was the BioPro Plus gaskets from Rubber Fab, from GYLON, and they were always completely clean after a standard cleaning in place process. And again, you can go further. You can verify those results. Like I said before, you can use, for example, a fluorescence microscope. When preparing the products beforehand, this fluorescence microscope might give you a pretty good idea of how contaminated a surface is. In this case of our gaskets, after they have went through a cleaning process, and we already saw the EPDM surface with a lot of activity, or activity of microorganisms. And then we also, of course, checked the gasket that had the best cleaning results, but we wanted to be sure that there went nothing wrong with the test. And what we actually confirmed was, by using the fluorescence microscope, that the surface is very clean with only very minor organic residues, which are very likely to represent fats. In this case, we can be very sure that there are no organisms because of the very specific shape of the test organisms used. They're like long worms almost, as you can see in this picture very well. So we have confirmed that the cleanability of GYLON Bio-PRO Plus was successful through all of our testing. And confirming further, looking into this further, we also see that the surface quality of GYLON Bio-PRO Plus, it's a lot smoother. Like you can see again, the scanning electron microscopic pictures here. We have, in this case, we have the ones that we have seen already before from other common gasketing materials, and quite big next to it, so you can see the difference. We have the GYLON Bio-PRO Plus surface with the same magnification, of course, and we can see that the material, because of its unique manufacturing process, really, it's very, very smooth. So it's very smooth, but not only that, it's also very dense. It has a very high density with a very low level of pores, a high smoothness, and these properties allow an efficient barrier for microorganisms and other molecules to adhere to the gasketing material. Also, we have discussed about gasket intrusion. So we have tested also the dimensional stability of GYLON Bio Line products. And we have also tested other products. And we saw that GYLON Bio Line provides the best results in terms of dimensional stability, meaning the gasket does not intrude into the system. We have a smooth bore connection, which ensures or which prevents that there are no dead spaces because of intrusion or recess, no risk for product accumulation, and ultimately no risk for bacterial buildup. Whereas the elastomeric gaskets, depending on the installation process for sure, tend to intrude into the system, and traditional PTFE gaskets show a lot of cold flow. In most cases, they show cold flow and creep, meaning when they are compressed, load is applied, they do not uphold the load, but ultimately they will creep, especially when thermal cycling is applied as well. And this again might cause that we lose the ideal sealing point when we remember back, because the compression is lost. And you don't have those problems with BioLine. So you have a gasket that has a absolutely reduced cold flow. It stays in place where it's supposed to be, and therefore it's the best material to ensure a smooth bore, easy cleanability, and is a hygienic connection.
Sasha?
Yes.
We have a question in the chat room, and I think while we had traditional PTFE next to GYLON Bio Line on this slide, it might be a good point of time to raise this question. So the question was that GYLON Bio-PRO Plus is 100% PTFE. So why is it better than a standard traditional virgin PTFE?
Oh, that's a very good question. I like that question a lot. I'm not seeing the chat right now, but I think I'm clear on the question, and I would like to answer this briefly because I'm actually sure this might be a good topic to go into detail further on, maybe at a different time. But let me describe briefly why Bio-PRO Plus, 100% PTFE gasket, that's correct, has a reduced cold flow compared to a traditional virginal PTFE. And the reason for that is the manufacturing process. Like I said, I can go into detail and also show you the process actually and the unique differences, but let me try to make it short for now and just explain in words. So the difference is the manufacturing process. Whereas most traditional PTFE is kind of compressed in a cylinder in its raw form and then sintered in a whole block. The GYLON materials are manufactured completely differently. With GYLON, we are talking about a completely different mixing process of raw materials and a so-called calendering process, meaning the materials are rolled out in enormous big calendaric equipment with a lot of force. They are rolled, then they are folded and rolled again, folded, and this step is repeated many times, which kind of results in a cross-linking of the PTFE molecules, giving the material an incredibly higher dimensional stability. It also improves the homogeneity of the material. For example, if you would insert fillers, they would be distributed more evenly, more homogeneous throughout the material. But even in our case of GYLON Bio-PRO Plus, without fillers, due to the manufacturing process, we have like a interwoven structure if we look at the PTFE chains. And this interwoven structure, because of the manufacturing process, it results into a very high dimensional stability, even though there are no fillers used. I hope this answers the question for now. Of course, we can definitely pick this one up and show you some more information on the manufacturing process and on why we know that the materials do not have the cold flow and the creep that other traditional PTFE gaskets show. Are there any follow-up questions on this one, Dominic?
No, it is answered for this moment. Thank you.
Okay, thank you. Very good question. I like that question. So, I mean, the question was a good one. It came at a point where now I would like to move to the actual product. So let's have a look at the product that I showed you was tested, that has passed all this internal and external testing with flying colors. And the product is GYLON Bio-PRO Plus. And GYLON Bio-PRO Plus is the ideal sealing solution for the pharmaceutical industries because it is compliant to 3A sanitary standards. In this case, standard 2027. It is compliant to all FDA regulations, both for extraction testing, formulation, and so on. Good manufacturing practice. It is USP Class 6 tested. Of course, it holds a lot of more certificates, a lot of more testing results are available, but let me point out those only at this point. We have a gasket with, let me say the highest sealing integrity. Like I said before, the GYLON materials, because of their unique manufacturing process, resist creep and cold flow very well, which in return eliminates gasket intrusion in the process flow. The product complies with ASME BPE standards. So it complies with the ASME BPE on dimensional stability requirements, which are laid out in the standard, initial fit-up requirements, again, which are laid out in the standard, and it was SIP tested according to ASME BPE. So the steam resistance was tested, and also the dimensional stability after long-term exposure to steam. So test results are available. We're happy to share them with you. The gasket is very easy to remove from the flanges with zero gasket residue. So there's absolutely no problem in maintaining the gasket, in replacing the gasket. You won't have to deal with dirty equipment. You have a residue-free removal. The gasket performs exceptionally well with thermal cycling and with chemical exposure. Chemicals, of course, aren't a problem for, let me say, most chemicals, but most chemicals we encounter in production processes for the pharmaceutical industry do not pose a threat to PTFE. Of course, there might be exceptions, but the gasket resists chemical and thermal cycling very well. Because of the extremely dense and extremely smooth surface, it is non-absorptive, like nothing sticks to the gasket, nothing adheres, and nothing is absorbed by the gasket. The PTFE itself, in its nature, provides an unlimited shelf life, which in the end can simplify the inventory, the stock keeping, and also gasket selection. It is ideal for steam in place and cleaning in place processes, and it comes with full traceability by default. That means the chain traceability from raw materials to finished product, but also the internal traceability with quality documents and certificates available. The gaskets also come by default with a batch number that is engraved to the edge of the gaskets, a unique batch number that allows full and easy traceability. And then at this point, I would also like to briefly introduce our GYLON Bio-PRO gaskets. In this case, they do contain a filler. We haven't looked at them so much in this presentation. They do contain a filler. So in this case, we do not have 100% PTFE. Here we have an expanded perlite as a filler, or also called aluminum silicate. It's an organic, natural, 100% natural filler. Also, it incorporates a blue pigment, which gives the Bio-PRO its characteristic blue color. Of course, it's the whole gasket is FDA compliant. It is also USP Class 6 tested. It was also tested according to European food contact regulations for plastic materials. It is manufactured according to good manufacturing practices. It also shows very, very good resistance towards creep and cold flow, so you don't have to deal with gasket intrusion. It complies to ASME BPE. You also have easy removal of the flanges with a very good chemical and thermal cycling capability, of course, because there's a filler. The chemical resistance is not quite as good as the Bio-PRO Plus product, but it's still very good. And you have also a universal shelf life because it's a PTFE-based product. The fillers won't change that in this case, and it performs exceptionally well with steam, exceptionally well with big pharmaceutical manufacturers having this gasket not only in the applications but also in their own testing facilities with steam exposure, continuous steam exposure up to 5 years without any physical damage of the gasket. So here you can see the two products that I wanted to show you today, that I want to recommend to you today, really, for the most critical pharmaceutical manufacturing processes. Thank you very much for watching. I hope that you have enjoyed the presentation and that the insights that I shared with you can be helpful to you in the future. Before giving the word back to Dominic for our closing slide, I would like to make a little announcement. in our webinar 6, so not the next webinar, but the webinar after that, we will launch for you our new range of elastomeric tri-clamp gaskets, which will also be announced in writing to you in the next couple of days. So I just want to ask you to stay tuned and to join us again for the next webinar sessions, where we provide more information on gasket installation. And in the last webinar for this session, for this season, we will provide more information on a new product range for elastomeric tri-clamp gaskets. So more interesting information are coming, and I thank you for watching. Stay safe and yeah, enjoy the summer really. Dominic.
Thank you so much, Sasha. It's been great knowledge once again, lots of information. I hope all participants see it the same way. Personally, every time I look at this presentation, and this is not the first time, I pick something new up, and I hope that it will help anyone in your customer conversations, customer calls. So let me share my screen with you for the closing slide. Today, we'll try something new in terms of feedback to this webinar, which is that we will use Microsoft Forms. And you can, I encourage every one of you to fill the survey after this discussion. It will not take more than 5 minutes. I just copied the link into the chat area. Other than that, you will find this link as well when we share the handout with you. Additionally, for sure, you can address any kind of feedback question to Chris, Sasha, and myself. Mr. Linker from ITE also raised another question in terms of the production process. We will pick that up also after this discussion in a personal conversation. So you will receive the training handout, and yeah, I will invite you and encourage you to also attend the next webinars. Today we finished the first of the second series, overall our fourth webinar. It's all about hygiene. Today, in 2 weeks' time, same time, 9 o'clock, we talk about gasket installation. And the secret for the 6th webinar was also just revealed, which is the elastomeric gasket range that we talk about in 4 weeks from today. And within today, you will receive another information in regards to these elastomeric gasket. So thank you, everyone. I think it was a really good series, and thanks for raising the questions. It's been interesting conversations. I wish all of you a nice weekend in advance, and stay safe and healthy.